Did everybody have a good breakfast this morning? Okay. We have I have two announcements first. First of all, we have a handout on the physics of karate, which is going to be the subject of today's lecture. Would everybody please settle down? And the second thing is that many people have come to Professor Redwine and myself with the freshman evaluation forms. These forms should be brought to your recitation section. They should not be brought to us. So you hand them into your recitation instructor, okay? Okay, so today we have a special discussion of some applications of Newton's laws to the physics of karate, And I hope will everybody please sit down quickly and take your seats. Everybody get settled, please. Okay. So, karate is an art, a sport, and it requires demonstrations. And so I've asked a couple of colleagues to join me here, and I'd like to introduce my colleagues now. Okay, come on out. Okay. So, this is David Feld, Alexandra Feld, and Jonathan Feld. Just a coincidence. Karate is something which everybody knows about. One knows about the Oriental connections with it. People have seen these demonstrations in which fabulous piles of bricks and blocks of concrete are demolished with a hand. And there's a lot of physics involved in that process. After all, how is it that a piece of bone can break a piece of concrete and not the reverse? It has to do with Newton's laws. It has to do with our understanding of various concepts of physics and mechanics. And one of the extraordinary things is that the ancient Oriental masters who studied karate as far as 2,000 years ago knew these secrets even though they didn't know Newton's laws. And I can tell you that if you study the motions which have been developed in karate, if you study the various techniques which have been developed, you find that they really use Newton's laws and the laws of mechanics in very special ways to make nearly optimal use of the human body. Now, may I have the first slide, please? I guess I can control these myself. I tried to have some slides today because there's a lot of material to present, and I want to be sure I have time to do that. First, I want to say that this lecture is dedicated to the memory of Ron McNair, our karate instructor and a graduate of MIT. May I have the next slide, please? Oh, I guess I can do this myself. Forward. Now, the knowledge of karate and the knowledge of the Asian fighting arts was actually also known in the West. And here's a picture from the Vatican Museum of two Greek wrestlers, Krugus and Damazenas. And this is a story which goes back to 400 BC. And actually, according to the legend, Krugus and Damazenas were two great fighters who wrestled with one another. And they wrestled all day and all night to see who would be the best, and neither could beat the other. And so finally, they decided that they would have a contest with each delivering one blow to the other. So first, Krugus elected to give a very hard blow to Damazenas' head, which he managed to withstand. And then he asked Damazenas then asked Krugus to raise his arm. And you can see here, the point of this story is the very fine spear hand strike, which was then delivered And without going into the anatomical problems which followed, suffice to say that Krugas came out the victor. I will eliminate some of the more gory aspects of the story. Okay. Now, let's see here. Next slide, please. I don't seem to be able to control this. Okay, that's all for the slides for now. So, now, we want to tell you about the physics of karate, and we want to tell you a little bit itself about karate itself. And we want to tell you something about the philosophy of karate also. As I mentioned, karate is an Asian Oriental art. It's practiced in all the different countries of Asia. Its roots go back 2,000 years or more. And it actually, modern karate, the word karate means empty hand, was a form of weaponless fighting which was developed in the island of Okinawa in the 17th century when the Japanese took over that island and prevented the soldiers and people of Okinawa from practicing their feudal combats. And so they developed this technique of fighting without weapons. It then was transferred to Japan in the early 1900s and has become very popular today. Karate is a purely defensive sport and a defensive art. It is not something which is developed so that you go out and beat people up. And as you will see, I will try to emphasize in various points of this lecture the very defensive nature of karate. And I also want to say that karate is also very important for developing mental concentration as well as physical strength. And the mental discipline in karate is at least as important as the physical aspects of it. So what we're going to do in this lecture is I want to show you some of the basic techniques. I then want to show you something very interesting, the central part of karate, which are called kata. They're very beautiful little dances, kinds of dances. We'll get into that. Then we'll discuss the theory and experimental aspects of breaking and some other things. So let us begin now by demonstrating some of the basic techniques with David and Jonathan. Okay? So now, the elements of karate, just like the elements of physics, are very well defined and very well focused. And there are many, many basic techniques, 70 or 80 of them. Hand techniques, foot techniques, head techniques. Any part of the body can be used as a weapon, but it's always used in a very special way. The most basic technique in karate is the front forward punch, the seikensuki. Okay? Now, this really illustrates many things about a typical karate technique. The first thing is that karate is totally different from Western sports. You know how we have all this follow-through and these wide swings and so forth and so on. Karate is completely the opposite. The ancient masters discovered that the most important concept was focus. In each karate technique, the idea is to develop the largest amount of velocity, the largest amount of force, and the largest amount of momentum, something that we just started talking about in the last lecture, to be able as quickly as possible to deliver a high amount of kinetic energy and then to transfer it to the target. Okay, let's demonstrate that at full speed. Okay. All right. Now, not only are there karate strikes, but there are also blocks for each technique. And the blocks are done in a very economical way. So now let us demonstrate how this kind of a seikensuki, oh yeah, do you want to do it to the face? Demonstrate to the face. Go ahead. Okay. I should also mention that black belts like this are very precise in their techniques. And it's expected that when demonstrations like this occur that there's just paper-thin precision in all of the moves. Okay, so let's demonstrate some blocks and counters. This is going to be some sort of an upper block. Go ahead. So notice, here's a typical example where instead of meeting force with force head-on, what happens is a certain amount of transverse force and transverse momentum is delivered to simply redirect the technique and render it harmless to the opponent. Okay? Now, Jonathan's going to demonstrate another technique, a hammer fist. This is a technique which is very effective in breaking piles of concrete, and David will show a typical block for that. Go ahead. Yes. 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 Okay. Now, there are many, many other kinds of karate techniques, and I want to emphasize that all of the parts of the body are used in these techniques. Let us just show you one kick. This is a very typical karate kick. It's called the side kick, the Yoko Geri. Go ahead. Now you can see here, it's delivered with the knife part of the, hello. It's delivered with the knife part of the foot to minimize the contact area, and the toes are curled to prevent them from being broken off in the technique. And there's a very large amount of energy and power which can be delivered in this technique. Okay? Go ahead. Okay? Okay. Thank you very much. Okay. Now let me show. Now I'd like to show some slides of some physical measurements that we've done over the years to be able to study some of these things. And this is actually a strobe movie that we made, where each of these techniques, this is a Seiken Suki, and each of these techniques was taken 1 millisecond apart. And then by just studying the position, we could study the velocity as a function of time. And you can see that in this particular technique, for example, the velocity rose. Here's the focus. Remember I told you there's very focused. The velocity is maximum at this point. And when the distance got to be about 85% of the way to the target, the velocity was around 7.5 meters per second. And now the mass of a fist is typically of the order of 1 kilogram. So that means 1/2 mv squared would be 1/2 times 1 times 100, or say 50 joules. So 50 joules of energy is being delivered in the time of maybe 1/10 of a second or a few hundredths of a second. So that's maybe 500 watts of power, which is an interesting amount of power. It doesn't sound like a lot of power, but on the other hand, it's certainly enough to break huge pieces of concrete. Next slide, please. I can't control this, yeah. This is a hammer fist, the same thing. Here we see velocities of the order of 10 meters per second. Next, please. These are, again, strobe movies. And here's just an example of an expert karate expert. Notice with a kick, you get of the order of 10 to 15 meters per second, with various kinds of strikes, 10 to 15 meters per second, and so forth and so on. So that gives us now a good piece of information as to how much speed and how much energy can be delivered in a karate technique. Next slide, please. Yeah, good. Okay, shut them off now. Thank you. Okay, so now the next thing is I would like to get right into this most central and to me the most interesting aspect of karate, the kata. And these kata are very, very wonderful things. They're very much like classical ballet. They're prescribed sets of movements in which the karateka, the karate practitioner, fights an imaginary series of opponents. And there are only a limited number of kata. For example, in the Shotokan style of karate, which is the one that we will be demonstrating today, there are about 50 kata. And each one of them has to be done in a very special way. There's the same kind of perfection. It's very, very closely related to ballet, I find. And in doing these, you're really never competing with anyone except yourself. And one can spend one's whole lifetime just constantly trying to perfect the kata, make them more and more beautiful. The other thing I want to say about karate is that it's a sport in which age, sex, and weight have no meaning at all, so that the tiniest person can be just as effective as a big, hulky person. So now let us demonstrate some kata. And first I would like to ask Alexandra to demonstrate the beginning kata, Takioka number 1. Alexandra? Alexandra, could you tell us about the very last part of the kata, what you did?
I am a practitioner of the martial arts. I bear no weapons. I pray I will not have to use my karate on anybody. But if I do, I am ready.
Thank you. Now, with black belts, the kata are more difficult, and I would like to now introduce another kata called Gankaku, which Jonathan is going to do. This is a kata which is, Gankaku means crane on a rock. The ancient karatekas, the masters, studied the animals and they studied nature, and in this particular kata, it's actually a kata which came from studying the crane. And I'd like you to try to especially look at this kata for the very end, where you will see 4 one-legged crane stances. Jonathan?
Gankaku, crane on a rock.
Now, as I was explaining, karate is really a very defensive art and a defensive sport. And one of the interesting things about the kata is that each of the 50 kata begins with at least one defensive technique before any offensive techniques are done. And in this particular kata, which we're going to show you now, David's going to do, it's called Basai. Basai Dai is a kata in which there are 42 moves, and you will see that the first 8 of them are defensive blocks. David. I'd now like to demonstrate a black belt kata, which is called Teki 1, to penetrate a fortress. It's a very strong, solid kata, and the motions are all in one direction. Teki 1. Teki Shoda. describes a lot of information about the physics of braking, and I'd like to present a simplified discussion here. There's a lot of interesting physics which goes on here. May I have the first slide, please? May I have the first slide, please? So the question we want to address ourselves to now is, if we have a piece of patio block like this one, which weighs 6.5 kilograms, how is it that a fist can actually break a huge block like this, let alone a pile of them? And we can also consider what happens in the case of a board. Okay, these are called 12-inch white pine boards. And you know, they're used for building houses. Maybe I should get the microphone here. Is this better? Is this working? No. So let's begin with by having a simple model of how braking occurs. May I have the next slide, please? Thank you. I think I better turn it on the light. So let's consider a block which is of dimensions L by H by W. This block will be impacted in the center by a fist or a foot or some other part of the body, producing a certain deflection D. Basically what happens is the block responds elastically, whether it's a piece of concrete or a piece of bone or a piece of wood. And when the motion, when the forces, the stresses inside the material reach a high enough point, then what happens is that breakage occurs, rupture occurs. Now, if you think about it, a simple approximation to this situation is that the block is like a mass, and that the mass has a spring on it, of spring constant K. You're experts on that. And actually, the mass is only half the mass of the block, and the reason for that is, roughly speaking, that only the middle part of the block is moving. The end parts of the block are simply supported, as shown in the diagram. And the fist is like a body traveling with a mass m, which is of the order of a kilogram, and a velocity v. So now, what happens in the braking process from this simple point of view is that initially the fist has a certain amount of kinetic energy, 1/2 mv squared, and it strikes the mass spring system. And a collision occurs in which momentum is conserved. As you'll see, it's not an energy-conserving collision, but it is a momentum-conserving collision, and we began to talk about momentum last time. And what happens is that at the end of the collision, before the spring has started to compress, the mass and the spring mass and the fist mass are together, and a certain amount of energy has been coupled into the target, which is called KE final, that we'll calculate in a moment. Now, once that final kinetic energy is in the target, it gets translated to the spring, turns into elastic energy, 1/2 kx squared. And when that amount of elastic energy is enough to break the material, then rupture occurs. Now, that breakage occurs when a critical deflection, d naught, occurs. In a moment, we'll talk about how you figure that out. So, what I want to first talk about is the step of coupling the energy from the fist into the mass. And it turns out that it's very important here to think about the fact that we have a very different physical situation. When we have a piece of concrete, for example, then the concrete, this one weighs 6.5 kilograms. The fist weighs a fraction of a kilogram. On the other hand, when we have a piece of board, the board only weighs 1/4 of a kilogram, and the fist is much heavier than that. It really affects the coupling of energy considerably. So let me just explain to you right away that kinetic energy is not conserved. I'll explain that right now. Let's use momentum conservation. You remember we talked about the fact that the momentum was the mass times the velocity. Initially, we have a fist with momentum mass times velocity. Capital M is the mass of the fist. At the end, after the collision has occurred, we have a total object of mass m plus m with a velocity little v. So we can easily solve for little v and get v equals m over m plus m. Now, the final kinetic energy is then the total mass times little v squared over 2. And of we substitute this V, then we immediately get that the final kinetic energy is equal to the initial kinetic energy, but reduced by a factor m over m plus m. So you can see that if little m, which is the mass of the block, is very small, then most of the kinetic energy is coupled in. That would be the case of the board. But in the case of the concrete, where little m is huge, then only a small fraction, maybe 20% or 15% is coupled in. And the rest of the energy goes into the deformation of the objects, mainly the fist. We'll talk about that a little bit later, or the part of the body. So finally, we derive a formula that the initial energy is equal to the final energy times m plus m over m. But then remember, we said that that final kinetic energy was going to become elastic energy. And so we finally have this equation that the initial kinetic energy, to be able to break the object, is equal to this mass ratio times the elastic energy necessary to stress the board to the point of fracture, or the break. Next slide. So the question is, how can we then calculate this critical distance, d0, which is the amount you have to deflect the body in order to break it? Well, now I have to tell you something about mechanical engineering. Here's the block again. And there are two parameters which determine the elastic and breaking properties of materials. One is Young's modulus, which is a bulk property which characterizes the springiness of a material without regard to its geometry. And then there's some sort of geometrical factor which depends upon the shape of it. Similarly, and Young's modulus has dimensions of newtons per square meter. It's a force per unit area. Similarly, sigma 0, the modulus of rupture, is a parameter which describes, again, in newtons per square meter, with a bulk material, how much stress you have to apply to produce what is called a strain, enough to rupture the material. Now, notice that if you think about it, the spring constant is related to Young's modulus because they both describe the springiness of the material. But we've got a very funny shaped object here. This is not shaped like an ordinary spring. And so it turns out that the relationship between the spring constant and the elastic modulus is given by this combination of length, width, and height of the block. And you can read more about that in the article if you're interested. On the other hand, in terms of the stress for an object of this shape, this stress multiplied by the correct geometrical factors then gives you the force that is necessary to break the object. So there's a certain amount of force necessary, which is proportional to the rupture modulus, and the spring constant is proportional to the elastic modulus. Now we can say that that critical deflection is just equal to the spring constant times d0. That's the force. Well, we already know the force, and so immediately we can calculate, see, we know k, we know f, so we calculate d0, and it turns out to be just the ratio of sigma to E, the modulus of rupture to the elastic modulus. And then we can calculate 1/2 kx squared, 1/2 kd0 squared, and we get this simple formula. So the bottom line is that the amount of elastic energy necessary to break the object is sigma squared over 12E times the volume of the block. But then remember, that's the amount of internal energy needed, but there's a coupling factor that we just calculated having to do with momentum transfer, and that means that the initial kinetic energy we need is actually equal to this mass factor times that, which can be much bigger. Much more energy is needed, especially in the case of a heavy object like concrete. Next slide, please. Next slide. So finally, I made a little table for you, and this table shows the parameters. First of all, I put three things here. Wood, that's the piece of wood I showed you. Concrete, that's the patio block. And then I've also put on a piece of bone to give you information about that. Now, notice that wood, in the units of newtons per square meter times 10 to the 8th, wood has a value of 1. Concrete is much stiffer. It's 20 times stiffer. And notice, just for interest, that bone is 5 times stiffer than that. So bone is a very elastically stiff material. Then in terms of the stresses to break it, notice that wood and concrete aren't all that different. But look at bone. Look at that. That's a factor of 50 different. So bone is a very, very hard material, much harder than concrete actually. And in addition, if we have time, we'll also talk about the effects of orientation, which can further say that to break a piece of wood takes a velocity of the order of 4 meters per second, which a beginner could probably do. And it takes an energy of around 6 joules. These numbers shouldn't be taken too accurately because there's much variation in the materials from piece to piece. On the other hand, it turns out that this analysis is a little bit simplified. To break a piece of concrete takes 8 or 9 meters per second. Only an expert could do it. And the amount of energy is about 9 or 10 joules. So much for the theory. Let's get into some experiment here. And I think that I will begin here by demonstrating a hammer fist strike of a pile of boards over here. So these breaking, as I told you, breaking is not an essential part of karate. And I want to explain that the only reason that we demonstrate these techniques is because of interesting physics. And it really shows the amount of force that can be put into techniques. I'd also like to ask during these breaking demonstrations for extreme quiet. Thank you. This is a hammer fist. Demonstrate a succession of techniques. First, a knife hand strike, and then afterwards a yoko-geri, which is a side kick to break some boards. let me just show the last slide here. Can you please give me the next slide? Oh yes, let me first show you in breaking. We actually had a strobe movie, and I unfortunately could not locate it. But here's a picture of a karateka, which is breaking a piece of patio block like the one you saw. And each of these pictures are 1 millisecond apart. And you can see that the fist is actually in is in contact with the target for about 5 milliseconds. And you can see that there's just 4 little dots that are placed on the fist that we can use for measuring the kinematics of the strike. And you can see here that even though the fist comes in contact here, that it's 4 or 5 milliseconds later that the crack starts to occur. And you can see that the crack actually occurs from the bottom. And the reason why the crack occurs from the bottom is because most materials are stronger in compression than in tension. And so it's actually this part that actually breaks always. Now we studied, it's really a shame that I couldn't find the movie, because in the movie you see that the fist really does not behave like a piece of bone at all. It actually behaves more like a rubber eraser. It completely crunches up. And then as the strike occurs, you see this pulse of muscle wave, which is going right up the arm, something which was extremely unexpected. There's the next slide. Now here we have calculated by just measuring the motion of that die. The displacement during the strike, this time scale is each square corresponds to 5 milliseconds. And now by taking the rate of change of the position, we can get the velocity. And then by taking the rate of change of that, we can get the acceleration of the hand. And you can see that at the time of the strike, the hand undergoes a huge acceleration of 3,000 to 4,000 meters per second. That's an enormous acceleration or deceleration. And it quickly comes to rest after that, or essential rest. And may I have the next slide, please? Next slide, please. Oh, yes, you can't hear me. And here's a picture. I wanted to show you a picture of actually some incomplete breaks. And here's what happens if you don't exactly hit the boards in the center. What happens is that, first of all, you can see that the wave motion actually goes to the center, but it's much, much harder if you don't hit it in the center to be able to do that break. And you can see the same thing here with concrete as you can with the boards. And also, it's interesting that here you can see that the hand has only moved down 2 or 3 boards, and yet you can see that the boards have been broken all the way down to the next to last one. And that shows that actually in a complicated situation like this, the first board actually breaks the second, and the second one breaks the third, and so forth and so on. Next, please. Finally, let me just mention, and in your article you can read more about this, that positioning is very, very important in karate, because the geometrical factors that I talked about before, which can be optimized to be able to protect the bone and to have a maximum effect on the target. And if you look at your handout, at the very end of your handout, you'll find that in fact, if you orient your foot correctly in a knife foot technique like this, that you can it actually becomes it takes 2,000 times as much force to be able to break this object, the bone, as it does to be able to break the concrete block. So bone is quite a remarkable object. So in conclusion, let me just say that I hope that you've learned a little bit about physics here. I also, I also hope that you learned a little bit about karate, and I hope that you will go away realizing that karate is not just something which is used to beat people up, but it really has many important aesthetic applications as well. Finally, I'd like to thank my colleagues for participating in this demonstration. Take all the broken wood and put it in a garbage bag for me. I'll come and get it. And,
Be happy to.
and if you have a fireplace, I'll share it with you.
I don't have a fireplace anymore.
So there's going to be two centers of activity. The breaking, which occurs later, is going to be done here. The Kata is going to go there in that little, on that black pad, and right behind it. So those are the two. Kata. You'll find out. I'll explain. Yeah, well, you can move around. It's no big deal. At some parts, yes. In some parts, no. You can, yeah. Okay, ladies and gentlemen, boys and girls, it's time to begin. I'd like everybody to sit down. Settle down. Did everybody have a good breakfast today, this morning? Okay, that's important. I'd like to make two announcements. First of all, there's a handout which you should be getting up at the top of the lecture hall. And secondly, many students have come to Professor Redwine and I and asked about the freshman evaluation forms. They should not be handed in lecture. They should be handed in to your recitation instructors. So the freshman evaluation forms in their envelopes go to the recitation instructors. Okay? Now today we have a special lecture which is going to discuss the applications of Newton's laws to karate. And one of the questions that we're going to talk about is how, could people please settle down, please? Just, okay? One of the questions we're going to talk about is how can a piece of bone break a piece of concrete rather than the reverse happening? I mean, of course, occasionally the reverse does happen, but hopefully it won't happen today. Now, so we want to discuss not only the kinematics of breaking and the dynamics of breaking, but we want to tell you a little bit about karate and some other things. So in order to do that, I've asked some colleagues to join me. Would you please come out?
Great.
Okay, I'd like to introduce David Feld, Alexandra Feld, and Jonathan Feld. Great. Now, we are all students of the martial arts, and I would like to begin by saying that our teacher was a man named Ron McNair. And may I have the first slide, please? And this lecture is dedicated to the memory of Ron McNair. Ron McNair was a graduate student in the physics department. He went on to become an astronaut. He was our karate teacher. And unfortunately, he died in the Challenger crash several years ago. And he was really a very special person. Next slide, please. Now, karate is a Japanese word which means empty hand. It's a form of weaponless self-defense, which was actually preceded by many other forms of weaponless fighting, which occurred in Asia and the Orient for more than 2,000 years. And the origins of karate were a mixture of religious, philosophical, and military. And interestingly, karate was not even limited to the eastern part of the world. Here's a picture from the Vatican Museum of depicting a story, a legend, which occurs 400 BC. It's about the two famous Greek fighters, Demosthenes and Krugas. And here we see Krugas fighting Demosthenes, and what happened was they fought all day long, and neither one could beat the other, these two great wrestlers. So finally, at the end of the day, they decided they would decide it by a single blow. And so first, Demosthenes said that he would like to strike Krugas in the head, and he struck a powerful blow, but Krugas withstood it. And so then Krugas asked Demosthenes to raise his hand, which he raised his arm, and here's the thing I want to show you, this knife hand strike, which he then delivered, and I won't go into the medical details, but suffice to say that Krugas won the battle and became the famous Greek warrior. So this shows that those ancient techniques were actually practiced in the West as well as the East. Now, they occur in all parts of Asia. They occur in Burma, China, India. But what happened was that modern karate was developed actually in Okinawa in the 17th century when the Japanese invaded the island and prevented the feudal practices which were then going on. So the Okinawans, in order to continue doing their sport and their fighting, they developed weaponless forms of fighting. And then in early 1900s, karate was taken from Okinawa to Japan, where it developed into a very formalized subject. Now, and I'd like to tell you, today we want to tell you a little bit about the study of karate. We want to tell you a little about the philosophy behind karate. We want to discuss the physical aspects of karate, of course. That's the most important thing. But I don't want you to go away, certainly, thinking that destroying objects is the important thing in karate, because it's not. Destroying objects is only a way of gauging the effectiveness of the techniques. And also, I don't want you to get the idea that karate is a sport or an activity which is done to be able to be a tough guy or to go out and beat people up. Karate is a very defensive art. It's inherently defensive, and I will explain that more as we go on. So in this lecture, what we're going to talk about is, first of all, some of the basic techniques, and then we're going to talk about the kata, which are perhaps the most beautiful and interesting part of karate, to me at least. Then we're going to discuss the theory and experimental aspects of breaking of objects, and then we'll discuss a few other things as well. So I would like to now begin by asking David and Jonathan to come out and demonstrate some basic techniques. So let us now begin by demonstrating the most basic technique in all karate, the front forward punch, seiken suki. Okay? Now, this is a good example of a typical karate technique. It's very, very different from the Western sports which are practiced. In Western sports, the first thing you learn is about follow-through in baseball or golf or boxing. But in karate, there is no follow-through whatsoever on almost every technique. Instead, there is focus. This technique is delivered with a high velocity. It terminates in a very short period right inside the target. And the focus is very important in imparting the maximum amount of momentum and force to the target. And the ancient Orientals who studied this had no notion of Newton's laws, but they still developed techniques which, when we study them by modern methods, we can see that these techniques really make nearly optimal use of the human body. So let's demonstrate that in a faster method. Okay. Now, karate techniques are also very highly prescribed, very formalized. For example, there are many, many techniques in many parts of the hands, feet, head, elbows. Many parts of the body can be used to deliver techniques. Even with the hand, there are many, many parts of the hand which can be used to deliver karate techniques. But each one is done in a very prescribed way. So for example, you can also do a front-forward punch to the face rather than to the solar plexus. Demonstrate that, please. Okay. Now, just as we have strikes in karate, we also have ways of defending ourselves against strikes. And now we'll have a series of, Jonathan will demonstrate some blocks which are used to defend the strikes. Go ahead. So this is a mid-body block, and you can see that here the principle is not to meet it with force on force, but instead to provide a certain amount of transverse force and transverse momentum which will deflect the oncoming technique and render it ineffective. Now, there are many, many other techniques, and Jonathan will now demonstrate a hammer fist strike, which is another type, and David will show how you defend against that. Okay? Okay. Now, as I said, other parts of the body can be used as well. And let us just demonstrate to you now one kick, the side kick, which is a very powerful technique, the yoko-geri, to the solar plexus. Okay. Now, let me just show you here for a moment. Notice that here again, this is a technique in which the foot is knifed in a position in which the very narrowest surface area is presented to the target. The toes are curled so that they're out of the way and not in danger of being broken off in the technique. And this can deliver a great deal of energy and momentum, as we'll talk about in a moment. Now do it at full speed. Okay. Okay. Thank you very much. Okay. Now, I'd like to have the next slide, please. And now I want to show you some measurements that we've taken of various karate techniques so that we could get some feeling of how much energy is available in a karate strike. And here's a picture of this is actually a set of strobe photos taken in Doc Edgerton's lab of a seikensuki, a front-forward punch, taken at exposures with intervals of 1 millisecond from one another. And then by just taking the location of the fist and plotting this as a function of time or plotting it as a function of distance, we can measure the velocity which is developed in this technique. And here you can see, for example, this particular technique had a velocity of about 7 meters per second at a distance which was about 85% of the distance through the technique and maybe 1 or 2 centimeters inside the target, which is just about right for karate techniques. So here you have a typical number like maybe 10 meters per second as the amount of velocity you can develop in a karate technique. And if you consider a hand, for example, the mass of the hand is a little bit less than a kilogram typically, maybe 7/10 of a kilogram. And so if we figure out the amount of kinetic energy which is available there, we know it's 1/2 mass times the velocity squared. Let's take the velocity as 10 meters per second. So 10 squared is 100 times 1 is 100 divided by 2 is 50. So typically there's about 50 joules of energy available in a karate technique when delivered by an expert. Can I have the next slide, please? Now here we have a hammer fist strike, in this case breaking some wood. And here again we've studied the motion here, and over a period of 100 or 150 milliseconds, which is a pretty slow, this is a slow technique but a powerful one, something like velocity of 12 meters per second was developed. Next, please. And here is a list of various techniques: the seikensuki, the hammer fist strike, a knife hand strike, various kicks. And you can see in each case that the peak speeds, which are reached right inside the target in each case, when delivered by an expert, are of the order of 10 meters per second. And there's some more information about that in your handout in case you're interested in more facts about that. May I have the next slide, please? Okay, fine. Enough for the slides right now. Okay, so now I would like to go on to what I think is the most interesting part of karate, the kata. And the kata are very similar to special types of ballet sequences of classical ballet. In the kata, the karateka goes through a series of motions in which he or she is protecting herself against a series of imaginary attackers. And the moves are highly prescribed, highly formalized. Kata are something in which you're only competing against yourself. You strive for perfection just as you would in ballet. It's a really way of trying to do beautiful things with your body, and some of the kata are quite beautiful. There are about 50 of these kata, and interestingly, every one of them begins with at least one defensive technique, and that's typical of karate, in which karate is really a defensive art. It is not an aggressive kind of an art. So let me now ask Alexandra if she will demonstrate the beginner kata takioka number 1. Alexandra, would you please do that? Alexandra, could you please tell us about the very last thing that you did in the kata?
I am a practitioner of the martial arts. I bear no weapons. I pray I will not have to use my karate on anybody. But if I do, I am ready.
Thank you. As you can see, there are many symbolic gestures in karate. And I also want to mention that karate is one of those sports where age, sex, weight, height are really no barrier. And in karate tournaments, the littlest people and the biggest people can all compete together depending upon their belt color rather than upon their age. Now I'd like to get into some more advanced kata. And I'd like to now show you a kata. Jonathan will show us a kata which is called Genkaku, which means crane on a rock. The ancient Asian karate masters studied nature and studied animals to understand much about how to optimize techniques. And this particular kata was actually based on the study of the crane. And I'd like you to look very, very carefully at the end of this kata. See if you can see the 4 stances of the one-legged crane. Jonathan?
Genkaku, crane on a rock.
Thanks, John. Now, we'd like to now demonstrate another technique. David is going to demonstrate a kata called Basai, Basai Dai. And Basai is a kata which really demonstrates, once again, the defensive nature of karate. This is a very powerful kata. And yet you will notice that of the 42 moves of the kata, the first 8 of them are purely defensive techniques, are purely blocks. So before any kind of counterattacks occur, the karateka makes an attempt to avoid any kind of conflict by making 8 blocks, and only after blocking his opponents and finding that he has no way out does he find that he has to go on the attack. David?
It's a linear kata, it's a very strong kata, and it's, again, a very defensive kata. Teki Shoda. I'd like to now talk a little bit about the physics of breaking. And in all the excitement, I forgot my notes. Let me go and get them. So let's discuss how it is concrete patio blocks like this certainly seem like massive objects. And it's hard to believe that a person can break one or many of them. And yet it's possible, and we should understand from a simple point of view of Newton's laws how it can be brought about. We have the first slide. It's just, oh, let me get the lights here. Let's leave that slide. So, basically, the problem of breaking is a problem of wave motion, of exciting waves in a block. And a block is really, can be considered to be like a violin string. But, and if you're interested in some of the details, you can read the handout, which discusses this in some detail. But I'd like to present today a sort of simplified picture of that, in which we consider it instead a problem of momentum transfer. And so basically, here's the idea. We have a fist, it's impacting on a piece of concrete or so forth and so on. And we want to understand exactly how objects break, what it takes to break them. May I have the next slide, please? So here we have our board, or block, with dimensions L, H, and W. And the block undergoes a deflection when struck with the fist, or with the foot, as shown here. And basically, as we'll explain in a moment, when that deflection reaches a critical distance, the object breaks. But I'm getting ahead of myself here. The first thing is that the object is an object which is elastic. If you think about it, even a piece of concrete has a certain amount of elasticity in it. That can be seen, for example, by taking a piece of concrete and tapping it with a hammer and noticing that it can support acoustical waves. So it does have some elastic nature, so does bone, and so does every property. And so in a sense, you can think of this problem as really like the problem of mass on a spring. That really this concrete block can be thought of as a mass of concrete on a spring of constant kick. And actually the mass, the effective mass, is only half the mass of the object. And the reason why is roughly because only the middle of the object moves. The ends are simply supported, as shown here, and they don't participate in the motion at all. So it turns out that if you study the theory, that only half of the mass comes in. And we have to figure out what the spring constant is in terms of the elastic nature of the object and its geometry. So basically we can sort of model this problem as a problem of having a mass, a fist, or a foot, a mass capital F, and velocity capital V, which is impacting on this spring and compressing it. So here we have drawn the picture of that, and I'd like to point out three phases of the process according to this simplified picture. In the first phase, we have the fist with an initial kinetic energy 1/2 mv squared, which is just about to make an impact on the block. In the second phase, before the spring has had a chance to compress, but after the collision has occurred, we have a situation where the two masses are essentially stuck together in contact, and the mass system now is moving with a velocity v, giving a final kinetic energy 1/2 m plus m times little v squared. Now that system can then convert this energy into elastic energy 1/2 kx squared. And when the compression is sufficient to compress the object to a distance d0, a critical distance that we'll talk about in a moment, then that amount of elastic energy will break the object. Now, I want to point out to you, we began studying momentum in the last lecture, and I want to point out to you that this is a process in which kinetic energy is actually not conserved, and I'll show you that very simply. The kinetic energy which is available here cannot all go into the object. And that really depends, to a certain amount, on the nature of the object. It really depends upon the ratio of the masses, as I'll show you now. But basically, you have a piece of wood like this, which has a mass of maybe 1/4 kilogram. This is 1-inch white pine. And you strike it like this, then the fist is much more massive than the wood, and that, as you will see, gives very effective energy transfer. But on the other hand, a heavy thing like this is a concrete patio block made of number 3 cement, and it has a weight of 6.5 kilograms. And so, because the hand is relatively light compared to that, the amount of energy which is transferred is very small. I want you to see that. The way it works is this. Let's just use the conservation of momentum. The initial momentum, you remember that momentum is just the product of mass times velocity. Now the initial momentum that we have is just the mass times the velocity of this object. But then this is still, so it has no momentum, v equals 0. But afterwards, when the two objects are stuck together here, then we have a momentum which is the sum of the masses times the final velocity. And of course, it's very easy there to find what that final velocity is, and it's just given by v times capital M over m plus little m. Now, the final kinetic energy is just 1/2 times the total terms of the initial kinetic energy, 1/2 capital M, capital V squared, the final kinetic energy is less. The final kinetic energy is less than the initial kinetic energy by the ratio of the mass of the hand to the sum of the masses of the hand and the board, which shows that if you have a heavy object that you're striking with, this fraction will be a very small fraction, indicating that very little of the available kinetic energy can actually be transferred to the object. Now also, notice that we can get, when we said that the final kinetic energy immediately could be converted into elastic energy. And so therefore I can solve for the initial kinetic energy, setting it equal to m plus m over m times the final kinetic energy, and then saying that the final kinetic energy then becomes the elastic energy, and get this very basic formula that the initial kinetic energy needed to break this object is equal to whatever that elastic energy turns out to be, multiplied by a number bigger than 1, which depends upon the momentum transfer between the fist and the object. Get the next slide, please. So now what we have to do is we have to figure out what is the spring constant of this effective system and what is the critical distance for breaking. Now, here we have to talk a little bit about mechanical engineering. And there are two properties which actually describe the behavior of a material like this. The first one is called the Young's modulus, and it describes the elasticity of the object. And the next one is called the modulus of rupture, and it is a measure of how much force or how much stress is necessary to break the object. And these are numbers which really are independent of the shape of the object. They just depend upon the material. So the Young's modulus E has units of newtons per square meter, and the rupture modulus sigma 0 also has the same units. And this one then has to do with what kind of springiness the object has, and this one is how much resilience it has to, how much forces are set up before it breaks. Now, you have to put in the geometry of the object to be able to get the quantities that you really need. So, if you take this Young's modulus, the elasticity parameter, and you multiply it by the appropriate shape factor, which is a combination of the length, width, and height of the object, then you find that the spring constant is just this Young's modulus times that combination. Similarly, for this particular kind of a geometry, when broken in the top like this, the amount of force necessary to break the object is just given by the modulus of rupture multiplied by these same parameters. Now, once we have this formula for F, and we have this formula for K, we can easily find D0, the critical deflection, by simply saying F0, which we know, is K that we know, times D0, and that immediately gives us that D0 is equal to some combination of dimensions times the modulus of rupture divided by the elastic modulus. And then we can say that the elastic energy required to break the block is just 1/2 K D0 squared, and that turns out to be this very simple formula, sigma 0 squared over 12E times the volume of the object. Now remember that we said before that this is the internal energy needed to break the object. But on the other hand, in terms of the initial energy available in the fist, we have to multiply with this factor of m plus m over m. So that's the basic idea of this simple picture. And may I have the next slide, please? I've just made a little table here to summarize for you what these parameters are for three things. First of all, the wood that I just showed you, the concrete that I showed you, and then some bone. So first of all, the springiness parameter, the Young's modulus. This is in units of 10 to the 8 newtons per square meter. For wood, it's about 1, but you can see that it's 50 times bigger for concrete. Maybe not 50 times bigger, but 20 times bigger. And so you can see that concrete is a much stiffer material than wood, which makes a lot of sense. But interestingly, you can see that bone is maybe 5 or more times stiffer than that even. So bone is an extremely stiff material. Furthermore, in terms of the modulus of rupture, you can see that wood and concrete aren't that different. But bone is enormously higher. That means it takes much more stress to be able to break a piece of bone. So now these are some of the clues that we're beginning to see as to why it's so difficult, why it's so easy to break materials with kinetic energy, according to this model, of about 6 joules. And remember, we estimated that in a good expert karate strike, there might be something like 50 joules available. So there's plenty of energy there. And notice that according to this model, it takes about 9 joules to break that piece of concrete, which is still much less than we have available, so it should be doable. I also want to point out that this model is really not terribly accurate. And if you read your handout, you'll find out that there are more accurate models. And in particular, the thing which is worst about this model is that it predicts that the velocities available to be able to break wood and concrete are fairly close. It turns out that with a more careful calculation, this is about right. It takes about 4 meters per second to break wood, which means that even a beginner can easily break a piece of wood. But it actually takes more like 8 or 9 meters per second of initial velocity to be able to break a piece of concrete. So that concludes the theoretical part of this. And now let's do some experiments to actually be able to demonstrate this. And I would first like to begin by demonstrating a hammer fist strike of this pile of boards over here. And let me begin by, again, emphasizing that breaking is not really an inherent part of karate. It's not usually practiced in a practice session. It's really not important. It's very showy, but the only reason that we do it is because we want to be able to gauge the effectiveness of the techniques, and also because it demonstrates some very nice points of physics from our point of view. The other thing is that these are rather difficult techniques, and so I would really like to ask for complete silence during the demonstrations that we're going to give now. So this is going to be a hammer fist strike of a pile of boards. Some of these concrete patio blocks afterwards with a hammer fist strike. sparring or kumites. And we'd like to just give you a little demonstration of that now, just to give you a feeling for how it works. Now, ready? Set? Hashime!
Yes! Yeah! Ah! Yes! Yeah! Yes! Ah! Yes! Ah! Ah! Yes! Yes! Ah! Yes! Yes! Ah! Yes! Ah! Yes!
Karate! Okay, have the next slide, please. I'd like to show you some still photographs of the strobe movie that we took some time ago to study in more detail what happens when a fist breaks a concrete patio block. You can see the concrete patio block here. These photos were actually taken in Dr. Edgerton's strobe lab. And here you can see that the fist has 4 marker dots on it so that we could study the kinematic motion of the different parts of the fist. And each of these frames, 1, 2, 3, 4, 5, 6, are taken 1 millisecond apart. And what you can see here is, I'm very sorry I don't have the movie of it because the movie is really much more dramatic than these stills. But what you can see here is that the fist is in contact with the block for 5 milliseconds. Then you can sort of see by this point here that there's an enormous deformation of the fist. And in the movie you can actually see that the fist really doesn't behave like a bone. It really behaves more like a blob of putty. And it completely distorts. And then as the strike occurs, you can see this wave of muscle pulse go right up the arm. It's really quite dramatic. The other interesting thing is you can see that the fist is in contact with the concrete here, but it's only 4 milliseconds later that the crack actually begins. And also you can see that the block cracks from the bottom up. And the reason for that is because most materials are stronger under compression than under tension. And so what happens is that the concrete breaks here rather than there. May I have the next slide, please? Now, one of those dots, I don't really remember what dot it was, we marked the displacement as a function of time of all of these different, of each of these dots. And from that, we can take the derivative. We can study the rate of change of that and get an idea of the velocity of the hand. And you can see here that the hand started at a velocity of 12 meters per second and it gradually decelerated to 0. And you can actually study the acceleration here by simply taking the derivative of that. You're experts in that. And you can see that the amount of deceleration which occurs here is quite enormous. Around 3,000 meters per second squared, which is really an enormous stress that the hand must undergo in decelerating so rapidly. Have the next slide, please. I didn't fully break the stack of boards today, and in this picture I also didn't break the stack of boards. And probably the reason is the same. Here you can see what happens when you hit the boards, not in the exact center, but off to the side slightly. And you can see that what happens is a kind of wave of destruction of broken boards occurs, and you can see it's trying to move towards the center, but here you can see that the bottom one didn't actually break. And there's another interesting thing that you can see here, and that is that even though the hand has only moved 2 or 3 boards down, that's 2 or 3 inches, you can see that the boards are broken well below that, maybe 8 or 10 inches below. And that shows that actually what's happening here is that the first board is breaking the second, and the second is breaking the third, and so forth and so on. And then you can see the same thing occurs in concrete. And here again, these blocks were not hit in the center, but it hit off center. And that produced a situation where the crack tried to propagate inwards, but then it was not possible to break all the boards because of that. Have the next slide, please. Then finally, I'm not going to have time to go into all of the details of this, but I just want to say that in addition to the rather enormous differences in the elastic properties of bone and the rupture properties of bone you can actually include the geometrical effects in the analysis along with the bulk properties, the Young's modulus and the modulus of rupture. And if you do that, if you look at the very, very end of the handout that we have, you will see that, in fact, a properly positioned foot like